Hello, this is a screencast for CME 650 at the University of Kentucky. This set of screencasts is going to discuss molecular theories of kinetics. The idea here is that we want to use kinetic theory and statistical mechanics to be able to predict as well as we can the kinetics of systems. The traditional view of thermodynamics is based on macroscopic observations, and these laws were developed based on macroscopic behavior. So, for example, this includes energy conservation, the first law of thermodynamics. Energy conservation is one principle that comes out of that. Another is entropy production, so the second law of thermodynamics, to state it as simply as possible. And of course, also with thermodynamics, we do things like look at the theory of non-ideal mixtures, look at how phase diagrams are developed, and so on. But it's all based on macroscopic observations and linking between them. The idea behind statistical mechanics, on the other hand, is to link microscopic interactions between molecules or within molecules to macroscopic behaviors. So the ideas are that we can get a molecular interpretation of macroscopic measurements. We can look at the macroscopic implications of interatomic interactions and answer questions of why we observe certain phenomena. So that's the basis behind statistical mechanics, or I guess the goal. And it's most mature for systems at equilibrium, which is what we're going to talk about in this series of screencasts. There are non-equilibrium extensions possible, but I will not be discussing them. Now I have to switch slides, sorry. Okay. So before beginning to talk about statistical mechanical theories, I want to talk a little bit about some of the underlying principles, which are based on probability. So, and a lot of what I'll talk about, you can find information in statistical mechanics books. The one that I used is Paul Houston's book, which is mentioned in the syllabus. It's published by Dover Publications, so it's relatively inexpensive, and it's a good, concise introduction. So, to talk about probability, statistical mechanics and molecular simulations use the statistics of a large number of particles. And we use probability as the basis for developing these theories. So I just want to make sure some terms are clear. If you've taken an elementary probability and statistics course, you probably have heard these terms before, but maybe it's helpful to go through them. So probability, first of all, is defined for a large number of trials, and that number is capital N. And if we assume that there's a discrete number of outcomes for a trial, and a lot of times gambling is used as an example. So if we, for example, talk about rolling a die, a six-sided die, every time that we roll it, that would be a trial. And there's a discrete number of outcomes. There are 6 of them. So if we look at the probability of observing a particular state, and don't get too confused by that, as I say, if we're rolling a die, each state refers to one outcome where the face is pointing up on a die. So the probability of seeing each one would be the limit as the number of trials approaches infinity of the number of times we observe that state over the total number. And probabilities are normalized. So if it's a discrete number of states, we can sum over all possible states of the probabilities, and it should add up to 1. So in the example I'm giving, if we roll a six-sided die and it's equally weighted, so there's nothing that would influence the outcome, we would expect an equal likelihood of observing any of the 6 possible states. So we assume that we have a probability of 1/6. Now if we roll the die 6 times, that doesn't mean that we're going to observe each state once. It means that in the limit of an infinite number of trials, if we roll 1,000 times, maybe 1/6 of those, we might begin to approach seeing 1/6 of those outcomes for each face. So that's the idea of a probability. Now if we know the probabilities of observing different states, we can calculate the average value of a function. And I'm just calling that A for now. So A is a property of the system that depends on the outcome. Now if we're rolling a die, maybe that property is how much money you get. Maybe someone's going to bet with you that if you roll a 2, they're going to give you 50 cents. So the value of this property would be 50 cents, and then for the other 5 faces it's 0. If we want to figure out the average value of the property, this is again for an infinite number of trials, it should be the sum over all states of the number of times we observe that state multiplied by the value of that property, and then we divide by the total number of trials. And that gives us, based on the definition of probability, the sum over all states of the probabilities multiplied by the properties. So what this tells us is that if we know the probability of observing a finite number of states, we can calculate the average value of any property we choose that depends on those states. So that's probability. Now another concept that's very useful for statistical thermodynamics is the idea of fluctuations and variances. So a fluctuation, if we know the average value of a property, the fluctuation associated with state I is the difference between the actual value for state I and the average value. So then we can calculate the average value of the fluctuation, or the average value of the difference between the property and the average value. And based on all the definitions that we have so far, that's just equal to the probability of observing state I times the actual value of the property in state I minus the average. And that's also equal to the sum of the probabilities times the value of the property minus the average value times the sum of the probabilities. This is normalized so that the sum of probabilities is equal to 1. And this first term is the definition of the average. So it's the average value of A minus the average value of A, which is 0. So the average value of fluctuations should be 0. And maybe this isn't too surprising because we can have positive deviations and we can have negative deviations, but over a large number of trials we expect those to go away. But there is a property that's a measure of how large fluctuations are that does not average out to 0. And that's based on the square of the deviations. And it's defined to be the variance. So the square of the variance sigma here of property A is the average value of the square of the difference between the property in a particular state and the average value of that property. So based on definitions, we can say that's the sum of the probabilities times the square of the difference between A of I and the average of A. And just carrying through the multiplication gives this second term, and that leads to this expression. And simplifying that, because we have the average value of A squared appearing twice, this is equal to the average of the square of the property minus the average value of the property squared. And so if we know probabilities, we should be able to calculate both the average value of the square of a property and the average value squared. So we can calculate what the variance is, and we can get a sense of how big the fluctuations are of the system. And that's useful for some property calculations. Now one thing that's going to come up is that our states of the system are not always discrete. So when we roll a die, in my example, of course, there are only 6 states. If we pick a card out of a deck, there are 52 possibilities. So there's a large number, but they're discrete. But if we want our state to define where a molecule is, so say just its Cartesian coordinates, there are 3 values of those coordinates, and they'll have units of length, but they're continuous. So a molecule can be located anywhere. So it's more useful to define a probability density, which is defined here. So if we imagine again that we have an infinite number of trials, or a number that's very large, we're approaching infinity, the differential of a number of trials that's going to be between a value of the state being I and a value of dxi is given by this probability density. So, and of course, we can really define our probability over certain intervals, which are going to be given by the integrals of this probability density. So the probability of a state being between x1 and x2 is given by the integral from x1 to x2 of the probability density function. Now what we can do with that, if we know that probability density function, we can plug it into our definition of an average and say what the average value of a property is. So for example, if A depends on xi, we take the integral, and if we're going to integrate over all possible states, we'll get the true average value of A. It's going to be the integral over all states of the property times its probability density. One example of a probability density that comes up frequently in probability and statistics is a Gaussian distribution, which is defined here. So this is a probability density, and it depends on the square of the difference between the property and its average value, and that's divided by the 2 times the square of the variance. And it's also normalized, which is this term in front. The standard deviation is proportional to the width of the Gaussian distribution, and it's defined from negative infinity to positive infinity. So if you remember what this looks like, you're going to have your average value of x, and it's going to be essentially a bell-shaped curve where it's going to have a maximum in the middle. Sorry, this is a poor drawing because of my stylus. This should be in the middle. And the width of it is proportional to the standard deviation. And this axis here is x. So that's one particular probability density function, but of course there are others that would be relevant. I can't draw any more here, so I will move on. Oops, wrong way. Okay. So the next thing I'm going to discuss is kinetic theory and collision theory, but to keep these videos from getting too long, I'm just going to stop here and come back to that later. So the next tutorial is going to be about kinetic theory.